Okay, welcome everyone. It's a pleasure to have you all here for the Thermalization and Quantum Information Workshop. As you might have noticed from the schedule, we have a theme for each day. So today is mostly focused on entanglement dynamics and the and advances in entanglement theory. Tomorrow is about the microscopic mechanism for thermalization, and Friday is about complexity and random ensembles. We're hoping to have a lot of discussion during the workshop. So we have 10 minutes for questions after each talk. And we also have a panel discussion at the end of each day, which will, the panelists will be speakers from the day, and it'll mostly be based on questions from the audience. So please think of questions and ask them.
Okay.
Yep.
All right, so we'll start with our first session. So our first speaker is Sagar Vijay from UC Santa Barbara. He will tell us about topological entanglement activity in a high temperature mixed state. Off you go.
Okay, everyone can hear me? The mic and everything? Okay, great. So thank you all for coming, and to the organizers for having me. Yeah, I'm really looking forward to interacting with everyone and to the workshop. Today I want to mostly talk about some work that was done in collaboration with a student, Yana Kim at UCSB, fairly young student, and a postdoc, Ali Levasani. Both of them were really a pleasure to work with. That'll be pertaining to the title of the talk, which is Topological Entanglement Negativity in a Thermal Mixed State, but at very high temperatures. The second part of my talk, if time permitting, will be about some slightly older work that's with a postdoc, Isabel Lovas, who's moving to ETH Zurich, and Utkarsh Agarwal, who's also at the KITP. Okay, so let me dive in. I was told to give some kind of broader perspective and background, given maybe a broader audience at this workshop. So I'm going to start with a few slides that are probably common knowledge to majority of the people in the room. So bear with me if that is the case. But I think it'll lay down the groundwork for discussing what I eventually want to talk about, which is mixed state entanglement, entanglement in quantum many-body systems that are open. Interesting patterns of entanglement there that can arise in some examples. Okay, so let me dive into part one of my talk. I really want to give a brief overview of entanglement in quantum matter as we understand it in some very coarse way without making, dwelling on specific examples. So we know that ground states of generic quantum many-body systems, gapped quantum many-body systems may have classical representatives that are disentangled, but in general will have some amount of short-range entanglement. And that short-range entanglement, its existence is sort of universal. And this is entanglement which we think of as being easily added or removed by starting with some kind of classical product state, by applying some kind of finite time evolution. So in the case of a gapped ground state that has some classical representative, we might think that any state in the phase which has short-range entanglement can be obtained by finite time unitary evolution with a local Hamiltonian starting from that classical representative. And in the case of long-range entangled states that still have some patterns of short-range entanglement, we think that that short-range entanglement can be modified by the application of some kind of finite depth unitary circuit, right? Okay, so when I discuss short-range entanglement, I just want you to think of it as entanglement that can be removed easily by the application of a finite depth unitary circuit when I talk about pure states. And of course, long-range entanglement also exists in ground states of gapped quantum many-body systems. And this means the opposite, right? That they are not easily preparable using these states, unitary evolution starting from some kind of classical product state and for finite time. So they're not preparable in sort of jargon by finite depth local quantum circuits. And these ground states are familiar to all of us. They're some examples of these ground states that are gapped are host topological orders, and the fact that they have patterns of long-range entanglement that are actually universal is
It's going to be straight and then to your.
Yeah. Okay. The fact that they have patterns of universal patterns of long-range entanglement is intimately related to the fact that they can host exotic excitations, right? So these can carry fractional quantum numbers like fractional charge, and they can have long-range statistical interactions, which give rise to exotic statistics in, say, two-dimensional topological orders, right? So this is kind of the coarse, to paint with a broad brush, picture of patterns of entanglement that can arise in equilibrium, zero temperature quantum matter, particularly in gapped quantum many-body systems, right? And a particularly well-known diagnostic of long-range entanglement in pure ground states is the topological entanglement entropy, which is also related to the quantum dimension of anyon excitations in 2D topological quantum orders, right? So the topological entanglement entropy is a constant reduction to the area law scaling of entanglement in a gap ground state, which you can think of as arising due to some non-local constraints. So in topological quantum orders, ones that are describable by gauge theory with a finite gauge group, that non-local constraint has to do with the fact that the excitations can be really thought of as charges or fluxes in a gauge theory, and they obey some non-local constraints. And that leads to a universal reduction in the entropy for large enough subregions, which is the topological entanglement entropy. And that can be teased out in some universal way, regardless of whenever you're inside this particular gapped phase. So these are things that are, I think, quite familiar to everyone. But I want to now dive into mixed state entanglement. So the entanglement of a mixed quantum many-body state. So a mixed quantum many-body state is now described by a density matrix. So a density matrix, of course, is to be thought of as some statistical ensemble of pure states. Of course, the decomposition into a particular statistical ensemble is not unique, right? And that makes talking about entanglement of a mixed state in general quite difficult, and particularly challenging when we're talking about mixed quantum many-body states. I want to define a few things. So how do we think of entanglement? So entanglement in a pure state we think of as witnessing non-classicality as measured by, say, the von Neumann entanglement entropy. But mixed state entanglement, or measures of entanglement that witness non-classicality, are very different. So obviously the von Neumann entropy of a mixed state clearly does not characterize how quantum the state is, right? And a trivial example is that the row that I've written on the screen could just be some mixture of classical states, and so you can think of it as really packaging for me the Boltzmann distribution for some classical ensemble, and there, of course, the entropy of that mixed state will, in general, have some, will be extensive, but in no way is that mixed state quantum. It's easily preparable on a classical computer and easy to sample from that distribution by just doing Monte Carlo sampling, right? But other measures, such as the entanglement negativity, characterize bipartite non-classical mixed state correlations. So this is a measure of quantum correlations in a mixed state, bipartite quantum correlations, which, when non-zero, tells me that that mixed state cannot be prepared just by doing local operations starting from a product state and classical communication across that interface. So this is the formal definition of the entanglement negativity, but it being non-zero to you should just be a witness of the fact that the mixed state across that bipartition is not preparable through classical means, okay? And the definition itself, I actually won't dive into too much, and we won't need too much for the discussion that I'm going to have, but this was introduced some number of years ago, I think, by Vidal and Werner. So this is a little bit different from the von Neumann entropy. And now, we could also talk about long-range entanglement in a mixed state, right? So any mixed state, of course, can be represented as a statistical mixture of pure states, but formally, you could define a long-range entangled mixed state as one which can never be decomposed as a statistical mixture of short-range entangled pure states, right? So of course, a trivial example of a state that is short-range entangled is the maximally mixed state, according to this definition. The maximally mixed state is one where the density matrix is proportional to the identity. Of course, that can be decomposed as an ensemble of classical states, right? It could also be, thought of as an ensemble of long-range entangled states as well. But that's the fact that there exists a decomposition which is classical in nature tells me that, at least by this definition, it's not long-range entangled. The remarkable thing is that we know that there are mixed states that are long-range entangled according to this definition. That is, there's an ensemble decomposition of the density matrix where none of the states can be thought of as being easily preparable starting from a classical product state. Okay, now the connection between this and the entanglement negativity may not be so clear. And this definition also seems like a very awkward one to work with, right? Because checking every ensemble decomposition of the density matrix to see if those states are short-range entangled is not really a feasible way to tell if a mixed state is long-range entangled or not. But let me summarize some things about mixed state entanglement that we have learned over the past, I think, several years. So since we are talking about thermalization largely in this workshop, and we will be interested maybe in Gibbs states of local Hamiltonians, so where a thermal density matrix is given by what's shown on the screen, it's important to maybe characterize what the nature of mixed state entanglement is in a thermal state, right? So one remarkable property, like I said, the ground state of a gapped quantum many-body system generically has short-range entanglement, right? So that's, it often has, we'll say that it has area law scaling of the entanglement entropy. But the Gibbs state of a local Hamiltonian actually is kind of maybe slightly different in a very interesting way. It turns out that the entanglement negativity of a Gibbs state of a local Hamiltonian necessarily vanishes above some large but finite temperature, okay? So that is, there is a large but finite temperature above which this state can actually be preparable entirely classically, okay? That's a fairly recent result. So that's often referred to as the sudden death of the entanglement negativity, and it's clearly different from how we think about short-range entanglement in gap ground states, where it just generically exists, okay? The second is that the entanglement negativity or the logarithmic negativity generally exhibits area law scaling in a thermal state, or it necessarily exhibits area law scaling in a thermal state with respect to a local Hamiltonian. And this is, of course, very different from the von Neumann entropy, which has volume law scaling in a generic thermal state, right? Volume law scaling for a trivial reason, right? For the same reason that a classical state has thermal state also has volume law entropy, okay? Great, so these are maybe two things that I want to emphasize. I mean, what's maybe universal about the fact that a given mixed state of a local Hamiltonian becomes classical at above a finite temperature, I don't think is fully understood. Now, there's you could ask if there's some non-local contribution to the entanglement that one can also talk about for a mixed state, given that we have measures of its entanglement as characterized by the entanglement negativity, right? And it is believed that certain mixed states belonging to certain phases, which I'm not going to formally define, exhibit the following kind of structure when you compute the bipartite logarithmic negativity for a bipartitioning of my Hilbert space into a region A and its complement, which is that there are states which will, to leading order, have some area law behavior of the negativity, but then they'll have some universal reduction of the negativity, which is independent of the bipartitioning geometry. And insofar as it's independent of that bipartitioning geometry, it's referred to as a topological entanglement negativity, a topological contribution. And it's believed that mixed states that behave as quantum memories have a non-trivial topological entanglement negativity, okay? And these are mixed states that are not necessarily thermal even, but they could just be pure states that have been decohered but are not thermal states. So this is a conjecture that hasn't been proven but has been observed in a variety of examples. The converse, though, is not true. That is, just because you have a non-trivial topological entanglement negativity does not mean you have a quantum memory, okay? And this is just known through a handful of examples. So it's just known by contradiction, okay? So exactly what the topological entanglement negativity is characterizing is a bit mysterious. At least if you were to ask me, I'm not sure what answer I would give, though there are experts in the audience that might say things that are maybe clearer. But okay, so there's a sort of one-way correspondence, whereas in pure states, topological entanglement entropy, since it's related to like any on quantum dimensions, et cetera, there's a sort of two-way correspondence, right? Great. So a very quick example, just so we're on the same page, and this is in work by Ehud, I guess, who's in the audience. So if I take the toric code, topological order in 2 dimensions, and I subject it to weak local decoherence. So I have my qubits in my toric code. I have single site local decoherence, say, as my model of decoherence. And then I obtain a mixed state as a result of that decoherence on the right, which I call rho, right? And you could ask, since the toric code has topological degeneracy on the torus, is quantum information encoded in that degenerate ground space actually recoverable, even though a noise channel has been applied, right? And this is the abstract, maybe question of quantum error correction. Is there a recovery protocol that exists that allows me to recover this quantum information in a protocol agnostic way, but just given this noise channel, right? And so I'm not appealing to the feasibility of this recovery by doing classical computations, but it turns out that just the existence of such a recovery process goes from, shows the following structure as you increase the decoherence strength. So when the decoherence strength is low, information recovery is possible, and above a critical threshold, recovery is impossible no matter what you do. So in some sense, you can think of it as the environment, which I'm discarding in this description, has gained access to the quantum information and therefore has decohered your state, right? Your logical state. So it turns out that the topological negativity of the decohered mixed state actually sees the same transition. So if you compute the bipartite topological negativity of this state on the right, it has a non-zero topological negativity contribution. It vanishes exactly when this quantum information theoretic phase transition also happens in this model for a particular noise channel, I should say. Okay. Yes. Yeah. So exactly. So the how you measure this is via the coherent quantum information. Right. Yeah. So I think later on in my talk, maybe there will be a better answer to that question. But basically, the coherent quantum information is related to how, if I think of this logical information as being encoded in some reference qubits, how those remain entangled with the system or become entangled with the environment as noise is applied. And that's all characterized by the von Neumann entropy. And the topological negativity is maybe a little bit different. It's just asking whether the final state is classical or not. So maybe it's easy to imagine that the final state can still be very quantum and hard to prepare, but you've still lost the quantum information. That's kind of very hand waving, but that's how I would describe it. Okay. So here's my overview after of the takeaways from this talk after maybe a 20-minute kind of broad perspective. So here I want to identify some new patterns of mixed state entanglement in thermal or thermalizing states by using some ideas from quantum error correction. And the first part of the talk, I think, which is probably going to be the majority of it, is a topological contribution to the entanglement negativity that persists in a high temperature state and how we can physically interpret it. The second part of my talk is thinking about some models of open quantum system dynamics where even though the quantum dynamics is open, so it's not the dynamics on a reduced portion of my system is not unitary, it turns out that there are dynamical regimes and phases where you can think of quantum information in the system as remaining in the system for a parametrically long time, and phase transitions where it's actually lost to the environment. So these are phase transitions that happen independent of what the steady state of the actual system is, which will always be thermal. Okay. Okay, so this is kind of the broad overview, and let me dive in. So let me just start with something that's completely different in an apparent way. So we know the equilibrium phase diagram of many quantum many-body systems, and the simplest workhorse of which is, say, the transverse field Ising model in spatial dimensions d greater than 1, right? So we know that there's at zero temperature a ferromagnet to paramagnetic symmetry breaking phase transition, and in dimensions larger than 1 that persists to finite temperature, right? So there's a symmetry broken phase that persists at large temperature, up to some critical temperature beyond which the system is disordered, right? I want to just think about this system, this kind of zero form symmetry breaking for most of my talk, all of it basically. So I'll just use this as my workhorse of that kind of paradigm for that kind of model, okay? So the question that I actually want to ask is the following. So let's say now, we have maybe many models, microscopic models for how thermalization of a subsystem can occur with respect to a Hamiltonian, which describes the transverse field Ising model with some strength of transverse field and at some temperature, right? That could be through just closed system dynamics. It could be because I have a system that's coupled to a bath and the symmetry within the system is actually preserved. But here I want to ask a very specific question. So if I consider a symmetric ground state in the ferromagnetic phase, which I'll take to be a GHZ state, right? What happens to this kind of long-range entanglement? We know that this GHZ state is a long-range entangled pure state. It cannot be prepared via a finite depth circuit starting from a product state. What happens to this pattern of long-range entanglement if the state now thermalizes with respect to the Hamiltonian h of g at temperature T? Okay, so imagine that I have taken this kind of path from, the path doesn't matter so much, but I have a quantum channel that I'm thinking about that takes me from the yellow dot here, which is the GHZ state, and it's a dynamics that takes me to the steady state of a channel which locally is thermal with respect to h of g at temperature T, okay? How is this entanglement presumably destroyed as I go to higher and higher temperatures, okay, is the question that I want to ask. And actually, the first part of my talk is actually going to be studying something that's a little bit more special, but I'll argue that these results might hold for a more generic pattern of thermalization. what I'm going to be studying for the first part of my talk is really the following. I'm imagining, again, that I start with the GHZ state, but I'm actually thermalizing with respect to really a classical Hamiltonian. So G is equal to 0. And I'm imagining, and I'll explain exactly what that dynamics looks like, although you will all probably know what that is. And I'm going to ask what happens to the entanglement negativity of the state that I initially started off with, the GHZ state, as I put it through a quantum channel whose steady state is one where locally the system looks like it's thermal with respect to H of 0, right? Which is just the classical Ising model in spatial dimension D, right? And we know that the GHZ state has topological has a kind of a long range part contribution to its negativity. It has a constant negativity. And that is basically for the same reason that the GHZ state has constant entropy for any bipartition, right? That's a witness of its long range entanglement. It turns out that, so here's the result, and I'll explain how this result actually arises. It turns out that if you compute the entanglement negativity for this mixed state, so the GHZ state evolved by this channel that thermalizes me with respect to H of 0 at temperature T, you find that the negativity for any bipartition is log 2 up to exponentially small corrections in the boundary of the system at any finite temperature, insensitive to the thermal phase transition. And it's exactly 0 if you go to infinite temperature. So this is, I'll call this a topological entanglement negativity, because this log 2 is independent of bipartition. It's curious because it's not a reduction to the negativity, which is normally how we think about topological contributions. It's an additive quantity, obviously, but it's still, to leading order, it's a contribution that's independent of A, okay? And okay, so this result actually holds even if I'm in spatial dimension 1, but if I consider an extensive bipartition where the boundary of the region is large, I'll still have the following, this result, okay? So this is maybe a little bit curious. So let me explain how this arises. And I think the reason this happens, I think, is maybe kind of interesting, or at least the way that we think about it in this paper. So first of all, let me describe what this dynamics is. So this channel that I'm talking about is really the Metropolis Hastings dynamics of a d-dimensional classical Ising model, right? Which is how you would do Monte Carlo sampling for this classical system on your computer, right? So what does that channel do? That channel measures the local energy, right, of this classical Hamiltonian, and then flips spins locally according to the Boltzmann weights of this classical Ising model, right? So it is, that explicit construction of this model tells you something, which is that the channel is what I'll call strongly symmetric, right? The channel measures the energy density and then flips the spins. So it explicitly preserves the symmetry, the Ising symmetry within the system that I'm thermalizing, right? That's actually very different than how thermalization generically works in a closed quantum many-body system, right? Where the symmetry within the system is not preserved. So I'm calling attention to this because I think this is a special feature of this kind of thermalization that might actually make this problem a little bit different than if I thought about thermalization where only the global symmetry is preserved, including the bow, okay? So let me first discuss, or just tell you what the answer is. When I think about long-range entanglement in the resulting mixed state that's spit out by this channel, which I'll call rho of T, okay? And by long-range entanglement, I mean, according to the definition that I had in like the first slide or the second slide, which is rho of T a convex sum of short-range entangled states? Can it be expressed that way, or can it not be, okay? And it turns out that it cannot be below the phase transition temperature Tc. The fact that it can't be is maybe kind of obvious, right? So below that phase transition temperature, you have a strong symmetry that's preserved, and then you also have long range order in a conjugate basis, right? So there's not really, you can argue from that formally that then rho of T cannot be decomposed as a convex sum of short range entangled states. But rho of T is actually preparable by a finite depth local quantum channel above Tc. So this is actually an even stronger statement than what I had before. So it's not just that rho of T is a convex sum of short-range entangled states. I can actually give you a channel that's a local quantum channel that prepares it starting from a product state above Tc. Okay, and maybe it's clear what rho of T is exactly at infinite temperature. So at infinite temperature, it's just the maximally mixed state subject to the fact that there's a strong symmetry in the channel. The initial state is the GHZ state, which is symmetric. So the final state at infinite temperature is just the projector onto that symmetric sector, right? And that's obviously a state that you can think of as being short-range entangled. There's a product state basis in which I can easily decompose rho of t exactly at infinite temperature. Okay. So this is the long-range entanglement properties of rho of t. That tracks the phase transition. But to understand the negativity, I'll actually do something a little bit different. To understand why the state remains entangled, which also, by the way, is just to reiterate, is telling me that rho of t is not the thermal state of a local Hamiltonian, right? Because if it were, it would have an entanglement sudden death at a finite temperature that's not infinite, okay? But it doesn't. It has log 2 negativity at any finite temperature, right? So, so maybe another takeaway from this is that 0 temperature entanglement plus some kind of thermalizing quantum channel can actually prepare for you the Gibbs state of what is actually a non-local Hamiltonian. Okay, so how do we understand this result that I flashed a few slides ago, that the negativity for the bipartite negativity is a constant and is purely topological in the system except at infinite temperature when it's 0? Well, I want to use the following fact. The entanglement negativity is what's called an entanglement monotone. And that means that given a bipartition, the entanglement negativity of a mixed state cannot increase if I do LOCC across that bipartition, okay? What is LOCC? LOCC is local operations in classical communication. So given a bipartition, I can call my one system A and the complement B, and the parties Alice and Bob that are allowed to do operations within those respective subsystems. LOCC involves local measurements within A, local measurements within B, any unitaries within A and B, classical communication of, say, measurement outcomes, but no operations that straddle the bipartition, okay? Now, it's obvious, that certainly that the negativity can decrease under local operations in classical communication, right? Because if I just measure out all of my degrees of freedom in both subsystems, of course, the system is totally disentangled. The fact that it's a monotone is maybe not so obvious, but it's known. Again, I think in this paper by Vidal and Werner. Okay, so I'm going to use the fact that the negativity is an entanglement monotone to ask the following question. Is it possible that given rho of t that you can actually use LOCC to recover the GHZ state, okay? And it turns out that the answer is yes, that at any finite temperature, but not infinite, there's actually an LOCC protocol that recovers and prepares the GHZ state with perfect fidelity as the boundary of the bipartition becomes large. And that's what gives a lower bound on the negativity. And we'll argue that that's actually the full answer. Okay. So this is maybe like an instance where what I'm trying to do is many body LOCC to try to prepare a target state, whose entanglement structure I really understand, and then to bootstrap that to say something about mixed state entanglement. That's maybe the philosophy here. Okay. Okay, and maybe this should be maybe surprising. It's easy, at least it was to me, but below TC, it's maybe obvious you can do this. You have long range order in ZZ, right? So, and each state in a decomposition of rho looks long range entangled. So each state is formally kind of GHZ-like. But above TC, maybe it's not so obvious that this is possible because you've lost the long range order in sigma Z, right? Okay, so let me show you how this protocol works. So what is the recovery protocol for the GHZ state, the LOCC recovery protocol? So Alice and Bob are the two parties that live within A and within B respectively, and there's a bipartition which is shown in red, okay? So rho of t is a state that's prepared, which is some convex sum of purely symmetric states because the channel is strongly symmetric, right? That's all that I will say about the ensemble decomposition of rho of t. But what is this LOCC channel? Well, Alice and Bob actually, what they'll do is they respectively measure the Ising domain walls within their respective subsystems, okay? So A and B will figure out where those domain walls live. Importantly, right, A and B, Alice and Bob, cannot measure the domain walls that live exactly at their interface, right? That's not allowed by LOCC, but they can measure everything within A and within B. That's what they do. And now, to prepare the GHZ state, what do they need to do? They need to annihilate the domain walls, right? And if they annihilate them well enough, then they can prepare the GHZ state. How do they do that? Well, Alice and Bob independently, without talking to each other, just annihilate the domain walls within their respective subsystems. And once they do that, what state do they have? Well, there's one of two possibilities, right? Either they've prepared the GHZ state, in which case we're kind of done, right? Or they have a state where there's a domain wall that lives exactly at their interface, right? Which they can't detect because we're doing LOCC, right? So now we have a decision problem that we have to tackle, right? Alice and Bob have to decide whether to apply, how do they determine which state that they have? Well, depending on the state, Alice and Bob may want to flip all of the spins in one subsystem, right? And so they have a decision problem that has to be solved correctly in order to deterministically prepare the GHZ state. Okay, great. So ultimately what they have is this problem. They've done a bunch of measurements, they can share the outcomes, and then they've annihilated these domain walls, and then they have to decide whether at the end of the day to apply this unitary transformation or not. That's it, right? How do they decide how to apply that unitary transformation? Well, I just want to draw an analogy which is maybe helpful to many of you. The decision problem that Alice and Bob have to solve is actually identical to the decoding problem of a repetition code that lives on the boundary of their respective subregions. Okay, and I'll explain exactly what a repetition code is, just to, although it's probably something that's known to many of you. So the one-dimensional repetition code is a quantum code, in which a qubit of quantum information is encoded in the following way: a physical qubit on the left, and the sigma z states of the physical qubit are to be thought of as product states of a logical qubit. So I've repeated the physical qubit, say, n times, right? So the all up state of n qubits is now thought of as the physical up state, logical up state in the sigma z basis, and the all down state of n qubits is the logical sigma z down state. So the representation that one might choose for the logical operators of the logical qubit in this encoding is the following, right? So script z, which is the logical z, is a single site sigma z. And then the operator that's off diagonal that takes you between these states is flipping all of the spins. So it's product sigma x on all sites, right? To make the analogy clearer, in Alice and Bob's problem, the logical operators of the two-dimensional subspace that's left over after their first round of measurements and feedback, before they decide what unitary to apply, are the following, right? So they are allowed to apply this off-diagonal operation, which is the unitary on A, which flips all of the spins in A. But the logical sigma z I can think of as the presence or absence of a domain wall between their two respective subregions, right? So that's like a logical 2-qubit Hilbert space, okay? Now, what do we know about the repetition code? Well, the repetition code under X dephasing, right? So sigma z, so it's the symmetry here, the logical X operator is product X on all sites. The behavior of the repetition code under sigma X dephasing is as follows. So I take some encoding of quantum information and I run it through a single site decoherence channel, which is shown on the screen for, say, every site of my n site system, right? And we know that quantum information recovery remains possible with respect to this channel as px is increased and until maximal, unless I do maximal dephasing, right? So maximal x dephasing would be when px is exactly equal to a half, and that's when decoding is not possible. And this is maybe seems like an abstract statement, but there's just a very simple concrete protocol that does this, right? That implements this decoder. And how you implement the decoder is, again, you measure the Ising domain walls in my system that are nucleated by the decoherence, by this dephasing channel. And that allows me to locate the domain walls. If I have a domain wall, I'll refer to that as a non-trivial syndrome of the quantum error correcting code. If I don't have one, I'll refer to it as a trivial syndrome. And again, we have a very similar problem, right? So here, there's no LOCC, but here I'm just trying to recover initial quantum information. I measure the locations of some Ising domain walls that are nucleated by this channel, and there are actually two ways that I can annihilate the domain walls to return myself to the logical qubits Hilbert space, right? And those two ways are easily shown. So I can take pairs of domain walls that are say along the green lines, and I can annihilate them in that way, and that returns me to the logical Hilbert space. And of course, I can do it the opposite way also, right? Which is to annihilate the domain walls on, by applying sigma x on the orange sites. But it should be apparent, I think, that these two operations, if they're not, if it's not delicately chosen which one to do, you may end up performing a logical rotation also, right? Because these two operations differ by the application of the logical x, right? So the decoder actually that works until, say, one of the decoders, I guess, that works until this threshold px is equal to a half is the decoder that chooses the recovery operation with minimum weight, right? It just says of these two operators that can return me to the logical Hilbert space, which one acts on the fewest Pauli operators. And that works in the large system size limit with basically asymptotically perfect fidelity, okay? So that's pretty simple. It doesn't require that much very intensive classical calculation. So what do Alice and Bob do? Well, Alice and Bob can do something a little bit more complicated, but very similar to the repetition code. They can do what I'll call optimal decoding. So what they do is they apply this unitary operation UA. So they flip all the spins in A according to the probability that they have state 1 or 2. So they take their measurement outcomes, and given those measurement outcomes, they ask what the probability is that the final state, given how they annihilated the domain walls, is 1 or 2. And according to that probability, they will probabilistically apply this unitary operation, right? So that's a quantum channel that they're applying. And it turns out it's easy to qualitatively see that this kind of decoding scheme works with asymptotically perfect fidelity. Because in Alice and Bob's situation, the probability of having option 1 or 2, so option 1, they've performed this measurement and feedback and they have no domain walls between them, or option 2, they have a single domain wall. The relative probabilities, so P1 over P2 that Alice and Bob compute, will necessarily scale exponentially in the size of the boundary of A, right? And the reason is that these probabilities are more or less given by the Boltzmann weights of the classical Ising model, right? I mean, they are given by the Boltzmann weights, right? Another way of saying that is that the energy cost of a domain wall is always extensive, right? The free energy cost changes at the phase transition temperature, but the energy cost is always extensive. And so the ratio of these probabilities is always either exponentially large or small in the size of A. And that's what allows one to do decoding, right? And sort of abstractly, quantum error correction or any kind of recovery works when given the measurement outcomes or measurements of syndromes. If you have a bunch of different options for how one might do decoding, the probability that you should apply one particular option to get yourself back into the logical Hilbert space, the probability that that a given option will recover the state that you want is sort of exponentially large in some parameter. In this case, that parameter is the size of the boundary of A, not the volume, right? It turns out that for this problem, you can actually write down the optimal decoding protocol explicitly and actually write down what the fidelity of decoding is, right? So you can actually write it as some funny looking expectation value in this classical Ising model and actually show explicitly that it goes to 1 asymptotically as the boundary of A becomes large. Another way of saying this, which is maybe a sort of hand-waving sort of physics way of saying it, I guess, is that of course, the energy of an Ising domain wall is always extensive in its size. And in some sense, LOCC has quenched the entropy of the fluctuating domain walls, right? So LOCC has sort of made it so that the sort of free energy cost of adding a domain wall is really the energy minus T times log 2, because there's just 2 options for what Alice and Bob have to do, right? So at any temperature, at any finite temperature, the energy always wins as I scale up system size. But at infinite temperature, I always lose, right? So that's kind of the sort of picture. Okay. So the negativity we've sort of argued satisfies now a lower bound, right? Which is that it's lower bounded because I can recover the GHZ state pretty well. But you can also show that for this Metropolis Hastings channel and the final state that I'm specifically considering, that there's actually an upper bound to the negativity. And that comes from some kind of convexity of the negativity that I'm not going to discuss. So based on the sandwiched lower and upper bound, you can declare that as A becomes large, the negativity is entirely topological and just depends on the size of the boundary. And this is borne out in numerics, which one can do for fairly large system sizes because this channel is classical in nature. So what you see here is basically the exponential of the negativity. But as you increase system size and go above the phase transition temperature TC, you see that with increasing system size, it always saturates to some constant. And you can also see that how it saturates to that constant is exponential in the size of this bipartitioning surface. Okay, so this is true in any spatial dimension. That you should imagine that there's a repetition code that kind of lives on the boundary that whose decoding problem is being solved. Right. Okay. So let me say maybe a few more things about this. So. You might think that these results are, one would actually conjecture that this lower bound actually would hold for any kind of strongly symmetric thermalization that thermalizes your initial GHZ state with respect to h of g when g is non-zero at a finite and non-zero temperature T. And the reason is that the decoding scheme that I'm using to recover the GHZ state is one that only uses the sort of universal fact that, I would, if I had to go out on a limb and say that an Ising domain wall costs a lot of energy, right? And the entropy of those domain walls can be quenched via LOCC, right? So a conjecture would be that this state, rho of GT, which is a state obtained from GHZ by doing strongly symmetric thermalization, never suffers the entanglement negativity sudden death at any finite temperature. Whether that negativity is topological is maybe a little bit more subtle. I don't have much to say about that. But the cool thing, I guess, is you can always perfectly, another way of saying this, you can always perfectly distill a long-range Bell pair from this thermal state, unless you're at infinite temperature, which is kind of neat. An alternate perspective, which I think is maybe making reference to some quantities that a lot of us have been thinking about recently, is that one can actually show an alternate perspective on why this LSCC is successful. One can show that this LSCC recovery is successful as long as the post-measurement state has spin glass order. So that is to say, you perform all these measurements, and let me forget about doing optimal decoding. I just ask if the post-measurement state has long-range order in a conjugate basis, but which is glassy. The sign of that order can fluctuate across different measurement outcomes. And if that order exists, then one can actually show that the fidelity of recovery is asymptotically close to 1. So it would be kind of interesting if these sorts of, this is maybe a matter of perspective or something potentially interesting. It'd be interesting if there was a way to connect post-measurement glassiness to some kind of many-body LOCC. In this problem we can, but I don't know if that's more generally true. So finally, let me say about this problem that LOCC might provide a broader tool for studying mixed state entanglement beyond just the example that I mentioned. So another kind of neat example is the following. I mentioned at the beginning of my talk that topological entanglement negativity is generally something that we believe exists in a mixed state when if a mixed state obtained from some pure state is still able to function as a quantum memory, then we believe it has topological entanglement negativity, right? And I told you the converse isn't true, and the converse isn't true for in at least a few examples we know now. But here's one that I'll mention, and it's in a paper that came out last year. So I take the toric code and I decohere it under a local noise channel, which is shown on the screen at every single site. Okay, the channel is just shown for lattice site J. So what I do is this is a correlated noise model. So I apply sigma x at some site J and sigma z at a site that's displaced from it by a lattice vector delta. Okay, it was shown in this paper that this model, this decoherence channel, or this channel applied to the toric code definitely shows a decoding phase transition. So the toric code fails to function as a quantum memory when P is sufficiently large. But the topological negativity of the mixed state is actually non-zero for any strength of noise, unless you're exactly, I think, at P is equal to a half. Okay. So the way this was done was just by some exact calculation. And I want to maybe offer a slightly different perspective on this. An alternate argument is that since this is a correlated noise model, you can actually show that there's an LOCC protocol that for any strength of noise deterministically prepares the toric code state, starting from this mixed state. So you give me this mixed state, and even though I'm not allowed to do any syndrome measurements along the bipartition, I can infer what the syndromes are because of the noise correlations and perfectly prepare toric code. Okay, so that means that of course the negativity of rho for this bipartition that I've shown on the screen is lower bounded by the toric code negativity. A similar upper bound argument can also be applied, and you can actually show just by using LOCC that for this bipartition, for any P, the negativity is exactly the toric code's negativity, without any decoherence. Another perspective, which I don't know how to rigorously argue for this, but is potentially interesting. Perhaps the LOCC-based preparation of the toric code is already enough to establish that bipartite entanglement of the resulting mixed state is at least as long range as the toric code. So hand-wavingly, I might say that if via LOCC I can prepare for you a long-range entangled pure state, right, then the initial mixed state I started off with should also be long-range entangled. Okay. I don't know how to connect that precisely to the existence of topological negativity in that density matrix, but at least it's true in this case. Okay. So I think I'm supposed to leave 10 minutes for questions, you said. Is that right? Okay. So here's part 2, and here's my 3 minutes of part 2. Okay, yeah. So I'm not too dismayed also, because this was part 2 is something that I think more people have heard. It's slightly older work. But okay, but let me just summarize this by saying that it would be interesting if LOCC were a broader tool to understand mixed state entanglement. It's kind of interesting that you can prepare maybe a non-local, the Gibbs state of a non-local Hamiltonian by starting off with pre-existing pure state entanglement and then applying a local quantum channel, and that also shows negativity that doesn't depend on bipartitioning geometry, et cetera. Fine. Here's part 2. Part 2 is a story that was, with Utkarsh Agarwal, who's a KITP postdoc, and Isabella Lovas, who was a KITP postdoc until recently and just moved to ETH Zurich. It's basically studying the following question. So I mentioned this many times. So, dissipation, can drive phase transitions between a phase where you have an emergent quantum memory and one where quantum error correction kind of fails. And dissipation can do that in an otherwise unitarily evolving system as well, where you think of the unitary evolution as doing some kind of encoding of quantum information, and the dissipation as trying to access that quantum information, and trying to access it before it gets too delocalized is maybe the phase transition that one might term a quantum coding transition. So one question one could ask, this is very different from the first part of the talk, but is definitely related to at least thermalization and quantum information, the broad topic of this conference, which is what are the regimes of open quantum many-body evolution which function as dynamical quantum memories? So active quantum error correction is, of course, probably the first example of this. Okay, toric code subject to a single round of local decoherence, which we discussed, is not a long time open quantum many-body evolution, but certainly exhibits this phase transition. The part two of my talk is really that there's a chaotic quantum many-body evolution in 1+1 dimensions, which is open, which is, you think of it as chaotic unitary evolution in the bulk of a one-dimensional system, but it also sees boundary noise, boundary dissipation. And this is a system that a dynamics, which though open, can exhibit a phase transition between a phase where initial quantum information remains in the system or gets lost to the environment as a function of dissipation strength. So the concrete setup is the following. If one considers a long chain of qubits where you think of the qubits as, say, being in some kind of product state, and local qubits in the chain are thought of as encoding some kind of quantum information, and then I want to evolve them according to some dynamics that is open, and you can think of the open dynamics as driving this competition between the qubits of quantum information maybe being preserved within the system or lost to the environment. It's natural to think of initial quantum information in this state as follows. Because I want to be agnostic to the specific state of the qubits in this chain, but I want to say that their state is somehow either localized within the system or lost to an environment, it's natural to think of these qubits as being actually maximally entangled with a set of reference degrees of freedom, which I'll call R. And the statement that I want to probe, or the question I want to ask is, what is the fate of this, these qubits worth of quantum information in some kind of open system evolution? And it turns out that a diagnostic of whether a recovery channel applied to system A alone can recover information that was initially in the state of these qubits, even though it's undergoing open system evolution. Whether or not that can be done can be answered by looking at the following mutual information. This is related to the coherent information, up to some constants. But since mutual information is something that more people are probably familiar with, I'll phrase it in that way. And it's kind of intuitive. It's just asking, do the reference degrees of freedom that are entangled with the system, have a large mutual information with the system at long times? Or is it the case that they've developed mutual information with the environment, not shown on the screen, in which case quantum information is actually lost? Okay. Now, this question has some, for certain kinds of dynamics, this question has an easy answer. So if I think of generic open system dynamics, so I think of local unitary evolution represented by a quantum circuit shown on the screen, and I have some kind of generic decoherence or depolarization that happens with a finite strength per unit time, then it's kind of easy to see that the environment, again not shown, accesses the quantum information in an order one time. And the reason is that in an order one time, the system will become volume law entangled, right? And it becomes volume law entangled with the environment, and by monogamy of entanglement decouples from the reference degrees of freedom. So for that reason, you've lost the quantum information entirely, right? But with boundary decoherence, so that is if I only have depolarization that's localized to within some finite length, near the left-hand boundary or near a right boundary, which I've not shown, then there can be a richer phase diagram as a function of depolarization strength. The phase diagram, which maybe I'll kind of conclude with, since I think I'm losing time, is more or less the following. So the dynamics now involve local unitary evolution, and in this case, depolarization with some strength P. And I'm imagining that a single unit in time of this evolution is shown as delta T, right? So I have a single round of local unitary gates and a few sites near the boundary that are depolarized, and I apply this. The evolution time of this dynamics is actually extensively large in the system. It scales linearly with system size. So this is a long time open system dynamics, and it turns out that even in this long time open system dynamics, there's a phase transition between a phase where the information about the reference degrees of freedom and the qubits that are entangled with remains entirely within the system or partially within the system if it's not delocalized, or it's totally lost to the environment. So the phase boundaries are shown as a function of dissipation strength and also time T over L in the dynamics. And one of these phase transitions can really be very simply understood in the way that I just discussed a moment ago. Basically, it takes a time of order L before the system itself becomes close to maximally entangled with the environment. And you might think that at very low dissipation strength, that's the point at which the system will disentangle from the reference. When that happens, the mutual information between the reference and the system goes to 0, and you see this red phase transition, this red line of transitions between a phase where information remains partially protected or is totally lost. The more interesting line of phase transitions is actually in blue, which maybe is a little bit unexpected. But we understand in random unitary dynamics without any openness in just closed system, random unitary evolution, that there's universal structure in the entanglement dynamics that one can understand by thinking about the entanglement domain wall, which is a sort of emergent statistical mechanics of entanglement in this space-time. And it turns out that the dissipation acts to kind of pin the entanglement domain wall and drives a continuous transition when T over L is sufficiently small, but still a constant, but as you tune the depolarization strength. That's this blue line of continuous phase transitions. And the interesting thing, I think, and here's where I'll sort of conclude, I won't discuss the nature of the transition. Hopefully the existence of these phases is at least kind of obvious just by monogamy of entanglement. Perhaps the interesting thing about this continuous phase transition is it can also actually happen in totally closed unitary evolution, where instead of a Markovian bath that's interacting with the left boundary of the system, I actually imagine that I just have closed unitary, I have closed system dynamics, just unitary circuit evolution. But I'm imagining that there are two halves of my system that are now weakly coupled. And I can tune the strength of that coupling. And at long times, which are not parametrically different from the thermalization time of a subregion, there can be a phase transition where initial local quantum information in one half stays in the system or is delocalized across the entire system. This can maybe the most interesting part about this is that this happens close to the thermalization time, which would be like an order L over VE, where VE is like the entanglement velocity, right? So okay, so let me just stop here and just leave you with this sort of summary. Yeah, thank you for your time.
So thank you, Sagar, for the nice talk. I will pass around the mic for questions. This is for the Zoom audience and recording purposes.
Can I ask a question?
Yeah, sure.
Hi, Sagar, this is Xiaoliang. Thanks for a very nice talk.
Sorry, are you on Zoom? I think I see. Okay, yeah.
I'm on Zoom.
Oh yeah.
Yeah. So I wonder what's the role of the symmetry in the discussion about the topological negativity? Like, is what you said, will that be true for all similar systems, like with a ZN symmetry?
Yeah, we think that it would be. But that's something we're still working out, but we think that it should be the case for systems with a on-site global symmetry that's and you think of a phase diagram where say that symmetry is spontaneously broken as you tune temperature, or you go from a phase where it's broken to one where it's disordered. If you start with the initial state that is long-range entangled within the ground state subspace of that Hamiltonian, we think that some similar result might hold. But that is something that we're investigating, but it would hold for similar reasons.
Okay.
So I had a related question. So for like that same part of your talk, we were talking about the thermalization with some like symmetry constraint.
Yeah.
So I should think about the thermalization process as being that like you started with this like symmetric superposition,
yeah,
and then you send it through some channels such that like the +1 sector of the symmetry thermalizes and the -1 sector thermalizes, but you don't touch the relative phase.
Yes. Yeah. You should think of it that way, I think.
So if I'm like comparing that to the statements you made about like the sudden death of the entanglement negativity, should I think of that as then being that like there's like an important distinction somehow between like the microcanonical distribution where like you have a fixed symmetry sector, and the grand canonical.
And so I think that there is certainly for this decoding problem, that's really important. We know that the repetition code, you can't do decoding unless you preserve the symmetry, which, strongly by the channel that's doing the decoherence, which is really important for us in doing this LOCC. So that would be my conjecture. So that, that is potentially, there's an interesting difference as far as mixed state entanglement structure is concerned when you talk about strongly symmetric or weakly symmetric quantum channels.
And do you think that could hold also at the level of without symmetries, comparing the canonical density matrix to the microcanonical? Could there one of these avoid this sudden death?
That's a good question. Yeah, that's a good question. I'm not sure, but I do think that if you, again, have a Gibbs state of a non-local Hamiltonian, there's not an obvious reason that you need to have this sudden death happen. That's at least one thing that we know now. But I don't have a solid answer to your question. Yeah. Yes. Exactly. Yeah. Right. No, exactly. So, so I'm saying the answer is potentially yes, but I don't want to hang my hat on it.
For thermalization with a symmetry constraint, do you have a sense of what would happen if you changed the symmetry? Like instead of doing 2D Ising, you did something like Newman-Moore that has a different set of symmetries, but it's still classical.
Let's see. I'm not sure. So Newman-Moore is a little bit tricky, I think, because okay, my again, going out on a limb, my intuition here is that the thing that disorders the classical Ising model or whatever, and we think of the space transition as being classical even when there's a transverse field, is that the domain walls proliferate, and that entropy is something that I'm able to get rid of in the LOCC, right? So you can think of other models that undergo symmetry breaking transitions at zero temperature that become disordered at finite temperature because entropy wins. So Newman-Moore is an example of this, right? Mm-hmm. Maybe it's the case that if you do some kind of strongly symmetric thermalization in that system, that somehow that mixed state is still entangled because you don't have to care about the entropy anymore when you do LOCC. But that's not obvious to me before thinking about it. I will say that I think this was Shelling's question also. I will say that we think a similar story holds when you just have global symmetry breaking and you consider strongly symmetric channels. And you start with an initial state that is long-range entangled within the ground state subspace. One thing I didn't mention also is that this result actually holds even if you don't start with GHC, but you start with a state that is long-range entangled. So there you still end up with a topological negativity in the resulting mixed state, even though it's not symmetric to begin with.
Thank you.
So are you thermalizing to the ground state of H Ising times the projector onto the Ising even sector? Can I think of the non-local?
To a ground state?
Not ground state, sorry, a thermal state of this non-local Hamiltonian where the non-locality is just coming from imposing the projector?
Yeah. So okay, it depends on the precise initial state you start with, but I think for GHC, that is more or less the state that you have. Okay. There might be some differences, but you should think of it that way.
And in that topological order example, there was some Y one-form symmetry that
no, there isn't actually.
There isn't. Oh.
No, so actually, that's a good point. So when you have Y decoherence in toric code, there's a line-like symmetry. But this ZX dephasing, there's actually no symmetry in the problem. There's just correlated noise. So yeah.
I see. And sorry, last question. If I have an infinite temperature state, which is just projector onto Ising sector is 1.
Yeah.
That doesn't have this.
That doesn't. That's a purely classical state.
I see.
It's a classical mixed state, right? And there's obviously an easy way to prepare that starting from a product state.
Hi. One thing I'm a little bit confused about is you're saying that a lot of your results hold for any sort of topological order.
Well,
at least with the.
I don't think I am, but.
The statement you just. Okay. Okay. I guess my question is how much of your results depend on the dimensionality of the defects in question? Like for instance, here you're talking about a GHD state with an Ising model, and the thing results in line domain walls,
right?
But in the toric code, point-like defects.
Sure.
So how can I?
Yeah, it definitely matters. I mean, like, so maybe a different way to maybe answer your question is, so there's an example, right, where we know what happens, like I mentioned already in this paper by Ehud and Ashwin and collaborators, where we know the optimal decoding threshold for toric code under X or Z noise, right? And we know the topological negativity vanishes at that phase transition point also. We don't yet have a way of actually taking the mixed state when you're in the phase where you have a topological negativity and given a bipartition, do LOCC to actually deterministically prepare the toric code. I actually don't know how to do that. That I think partially has to do with what you're saying, which is that the defects that are created by this noise channel are point-like and not extended objects. They're a little bit harder to detect. Whereas Alice and Bob definitely use the constraint that domain walls can't end, innumerable times in order to do the decoding. So that is related, but I can't make that too quantitative yet. There's potentially an interesting example of 3D toric code because the fluxes are extended objects, but that's something we're still working on right now.
Hi, thanks for the talk. In principle, the negativity only gives a rigorous upper bound on the distillable entanglement. So when you have this log2 negativity, do you have like a protocol for actually distilling the delta?
So this is done through an actual protocol. So we actually compute the fidelity of GHZ state preparation with this protocol, and you can actually compute that it goes to 1 asymptotically as. So this is constructed.
Okay, sure.
Yeah. So this log2 is distillable. Yeah.
Okay, so no more questions. Let's thank Sagar again.